So the way we go about solving this problem is we recognize that there's only one number in here, and it says it's reacted with an excess. So whenever it's an excess, it means that number isn't going to matter. The next time that we get into learning, this isn't going to say excess, and you'll have to figure out which one matters. But whenever it says excess, it's really straightforward. You always start with the only number in the problem. And went ahead and got the molar masses for those ones. Sometimes they'll be given, sometimes you have to calculate it. And then we're going to do the reaction. So in this one, chlorine is -1, and the little 2, that means that the Fe had to have been 2+. That's why we would have had a 2 down there with the chlorine. And the NO3 is minus, and so this formula being right, that means that the Ag must be plus. Remember, these are transition metals, so they can kind of have a little bit of variability with them. So you just look at what they're bound to, and that's how you know what their charge is. And then we have FeNO3, because I swapped the negatives parts, and AgCl. Now in these double displacements, the metals don't change charge, and so we have to match everything up with the charges they had on the left-hand side. So there were 2 of those, and then this one comes out neutral. So I'm going to put a 2 in front here, and then I'm going to put a 2 over there. All right, so what I'll do is we're going to take 3.0 grams of FeCl2, and we're going to go from grams of FeCl2 into moles of FeCl2. And then if we're trying to find out how much AgNO3 was used, like we have to move from talking about this FeCl2 to talking about the Ag. So moles of AgNO3. And this should actually specify, but it should have said in grams. I'm sure it did on your problem. Oh. And so I'm going to go from moles of AgNO3 into grams of AgNO3. And once I get done, that number I get, that gram number, remember the word we use for that is theoretical yield. So it's yield because that's what we're making. It wasn't, and now it is. And it's theoretical because it's kind of like perfect conditions, everything perfect, assuming the reaction works perfectly, which never really, really happens. It's like the standard to meet. And then we just go and we grab these numbers. So this is, I'm going to take out that one because you don't have the one, 126.75, and that's in 1 mole. Remember, that's an understood 1 mole. And then I'm going to jump over and put the other molar mass in over on the right, 169.87. And then I'm going to look at my coefficients. And so I've got 2 of these to 1 of those. So 2 to 1. Always double check that you wrote that in right. And then I'm going to do my math. Whoops, I've got to be able to see my math. 3.0. I'm going to go across the top. Times 2 times 169.87. And I'm going to divide by that 126.75. So that gives me, I'm going to double check my sig figs. I believe that there were 2. There's 2 sig figs. So that gives me 8.0 grams. Now, a second ago, I called that my theoretical yield, but as I'm looking at that, I'm thinking, oh, wait, I actually was thinking ahead about the next problem. Right now, this is something that you have. It's not a theoretical yield. This is just the amount of reactant needed. And the next problem, you're going to do the same problem, but you're going to do it so that you're solving for the product of AgCl, which is a solid, by the way, and then that will be your theoretical yield.